Welcome back. Today I want to do a dive into functions in a new way. In particular, I want to set us up to describe what it means to have different sizes between two inputs and outputs, and to describe the kinds of computational advantages that observing different sizes can help us have. Take, for example, the situation I have behind me. Here I'm trying to fill customer orders. Each time I make an order, I assign it to a client. I could call the function lookup inside of a program, but I'm interested in studying a broad class, so we'll go ahead and start abstracting these by calling the inputs type A and the outputs type B. You could watch our video on functions to recall how we type functions and what a function really is. If you have a function that takes inputs of type A and outputs values of type B, and you're given a value A, well then you'll get a value B. We have some rules to substitution. The good news is the computer knows those rules and it will execute them. What are the pieces? Well, the f in this case is the function we just created. We called it myfunc. And the value A is what we give to myfunc. And the value B is what it came back, the f of A. It's behaving just the way we want. Notice that if all we saw in our code was line 6, we could be certain that B had type capital B, but we wouldn't know how it was made. That's the key to encapsulating any data type. We can hide the program behind a name like myfunc, and no one can see the details of our clever algorithm, but we can still sell them the product we've made. In our situation, what do we notice? If we start with any particular client, we can guarantee that there is an order to match it. Otherwise, they wouldn't be a client. Standing back to see this in abstract form, we could be describing a class of functions f from A to B with the property that for every little b of type big B, the equation f of x equals b has at least one solution, little x, type big A. This is such an important property that we've given it a name. Mathematicians call this surjective. Many textbooks would have called this onto. The word surjective comes from two parts. Sur means on, and jective will be a keyword for something like function or arrow, and you can see where it would be coming from. We'll see two other families of jectives. One will be injective and the other one bijective. We'll wait for those in another video. I'd like to study what advantages this observation has on building computations with surjective functions. To do that, I want to think about solving this equation. Since there's at least one solution, solving for it would be a sensible thing to do. If I look at this story problem, I might think about what I would want to solve for. Remember, each order is assigned to a client. No client exists unless they've made an order. This is what the surjective law came from. However, when I look at a particular client, nothing prevents that client from having multiple orders. And if they call me up on the phone asking for help, I'll want to be able to fetch one of their orders. In particular, the most likely scenario is that they're calling me about their last order. So a sensible tool for my software might be to have such a command. Since every client is guaranteed to have at least one order, last order is always going to return something. Another model might want to find their first order. For example, we might want to know how well this client has stayed with us in the past and treat them appropriately. Whatever your design models are, this is where you have the creativity to answer questions in a way that's appropriate for your story problems. I'm just illustrating with one example. Notice what's happening with my last order. The last order function is starting on the client side, and it's ending with an order. It's going from B to A. However, as we've already stated, there's no hope that we can generally say that there's only one order per client. So whichever order we pick back, it's simply reversing some part of the orders already made. So let's write that as an equation. Whatever we do with our last order, if we do the lookup, it must provide us with the same client. Notice this property would hold for many other choices other than last order. For example, I could have used first order or most expensive order. Whatever method we do to look up an order, what we're doing is we're serving back one of the possible ways to verify this was a client. We're not interested in servicing somebody who hasn't actually spent money in our company. This rule now is an equation that we can put into some of our testing of our software. You would call this a unit test. Unit tests can be done in multiple ways. For example, we could sample some random clients, create synthetic data to test it on, or we could use type theory to verify it with our compilers. That topic is a long, deep subject, and you can do a deep dive on the web to learn more about this. The result is that we think of this property as an abstract quality about all surjective functions. Let's write that. Capturing this in abstract language, we're now saying that the original definition of surjective is interchangeable with the second definition. That means a function from A to B that has an associated function /f from B to A, where, given any possible output, f/f of b equals b. In our story problem, this guaranteed that every client had at least one order, possibly many. A quick alert about notation. /f is suggestive notation. It's there because when we write an expression like f/f, it reminds us of other fractions we've seen in life, like 2/2, which turns into 1. If this was the number 1, we wouldn't be surprised that b was left unchanged. However, most functions don't have some kind of fraction notation. That's simply only true of fraction numbers. Here, for example, there is no such thing as 1 over a client. The notation is here to remind us of how the function should be applied. It should be applied as reversing f on one side. Because it can only reverse f on one side, it has a weird name. In the literature, this is known as a right inverse. Whether you call it a right inverse or you give it a more descriptive name based on your story problem, the result is that a surjective function always has one of these, and that's the constructive piece that we can add to our programming languages to help us check things. Unfortunately, there's not in general a unique right inverse. There can be many, and therefore we might even struggle to find one that's computationally feasible. Knowing that a function has a right inverse is not the same as having code that can do it. So simply observe that this is one of the many ways we might aspire to use a surjective function in code. It doesn't guarantee that every story problem that has a surjective function has a convenient version. There's one other way we want to think. When we study surjectivity, we'd like to find it in our story problems. And one of the ways that we communicate many of our ideas to each other is through diagrams. Can our diagram equip us to learn about surjective functions? Yes, it can. So let's imagine how we would describe this with the diagram. We have two possible ways to think about the problem. On the first one, we have an equation that we're trying to make equal. On the second one, we have a pair of functions that have to satisfy an equation. Both of these are hints about a diagram in the background. Not just any diagram, but a commutative diagram. And that's because commutative diagrams are flowcharts in which any two paths that start and end at the same place lead to an equation. These equations are the things we're after in the end. We have an equation here and another one here. So by whatever method we come up with, we'll want to decompose our diagrams into such equations. Now, as we've already mentioned, it could be impossible to come up with a particular function /f, and it wouldn't be unique anyway, which makes it difficult to use in a diagram. But there is an alternative. What we want to be able to do is apply /f before f and get rid of the effect of f. We could write that with the diagram. To get us started, let me imagine a square like this. I put my function f in two spots. It goes from a to b in both places. But now what I do is I go from there to someplace new. I go from b to c using a function u. But I also allow myself to go from b to c using a function v. If this is a commutative diagram, I've just planted an equation into our minds. Leaning on our notation of multiplication, it'll be easier to abbreviate this without the composition symbol and just put our two letters next to each other. If we actually had a /f, that is, a right inverse, we could multiply both sides by that /f. It would turn it into 1 and leave us with u equals v. The result is, the way we need to continue our diagram is simply to write that equation. It turns out that our two functions started and ended at the same place, b and c. The fact that f was surjective captured the idea that once we drew a diagram like this, we were able to conclude that bu and v were in fact the same function all along. This may seem impossible. After all, we had u and v be called different things. But remember, we drew this picture to be a commutative diagram, which was hiding an equation in the background. It's only after inspecting that equation that we discovered we could only have done this with an equation to start with. U had to equal v. Whether you like the word onto or you could transition to the word surjective, these three interchangeable definitions are essential for anyone dealing with functions. You can think of it with examples, or better yet, think of it purely abstractly. In the first case, we want functions from a to b with the property that for every output b, there is at least one solution x that reaches b. Alternatively, we want to have a right inverse, that is, a /f function, which, when applied to the inputs before b, will undo whatever b is going to do to the outputs. Lastly, you might think of a flowchart. If you start from a and go to b and then to c using two alternative paths, then in fact, they were the same path all along. You just didn't know it. Each of these teaches us a little bit more about the concept of surjective. Now let's pause to notice a consequence of this definition. Let's imagine that a and b have sizes. Since every b has to have at least one solution from a, we're forced to have a be at least as large as b. Remember, we use absolute values around sets when we want to think about their size, that is, their cardinality. Surjective functions are required to have this property in order that they can have the equation 1 solved by at least one solution. In fact, in most standard set theories, you can prove the reverse. If the size of A is strictly bigger than B, then there will be at least one surjective function from B to A. That's how mathematicians begin to decide how big a set really is. They place a surjective function from one to the other. As we go forward, we'll want to look at other situations. For example, what if the equation f of x equals b has at most one solution, or exactly one solution? Each of those will lead to a new family of functions, which is essential for both programming and applications. Until next time. That's how you take care of your chalkboard.